This one looks, these look kind of tricky. Do you want to try this one?
Yeah, okay.
Okay, this one uses isogonal conjugates. This one looks a little hard, actually. Let me see if this one might be a little easier. I'm going to erase what I did so far. So Stefan and I were talking earlier. Let's say you have 4 points on a circle and they have a cross ratio. Can you project through a point that's not on the circle? And
if you projecting through 4 points on the circle to 4 points on the same circle, then you can do it.
Even if the point you're projecting through is not on the circle, right?
Yeah.
Okay. Yeah, my solution to the G4 from the IMO shortlist did that. So yeah, I just want to make sure I could do that. All right. So, oh, actually, we're going to draw the 3 altitudes. So we might as well just do it like that. So D, E, and F are the 3 altitudes. M is the midpoint of BC. And then we draw the circle with diameter AH. Okay, this is kind of like a, and it meets it at Q. So Q, H, and M are collinear, that's well known. All right. ME and MF, we know those are tangent to the circle. So we want to see where do they meet the line through A parallel to BC. All right. So basically we have the 2 tangents. So yeah, these are actually all tangent. That's tangent to the circle. And then these are both tangent, which is well known. It's an easy angle chase. And it meets at E prime and F prime. So this is going to be F prime. It's going to be E prime. And QE prime and QF prime meet BC at S and T. Okay. Let me move the figure over a little bit. So we have S and T. So this is S. And this is T. And then it says, suppose that AM meets the circle again at K. So yeah, I'm going to make this picture much better in just a little bit. But this is K. And the circumcircle of 80K meets sorry, let me move this away. Meets it at W. So it's that point right there. Wow, this is a hard diagram. So this point is W right there. Show that SETF. So SE. This picture is so messy. SE TF and the tangents at Q and W concur. First, let me hide a bunch of stuff, but that might make me feel a little better about this. Okay. Now I'm like a little less scared. Just only slightly. Let's see, S and T. This is tangent. This is where AM meets it. There we go. Yeah, it does look hard. SE, let me just see what it's saying to do. SE TF. So TF intersects like right there, and then the tangents at Q and W. So yeah, maybe so let's let SE and TF intersect, and then basically we want to show that. I guess there's a couple different ways we could phrase it. Oh, it looks like TH and F are collinear. I don't know if that's obvious. Let's see if that's true. No, that's not true. It's not true. Yeah. Because then by symmetry, the other would have to be true. So yeah, you're right. This problem looks scary though to me. Do you want to try another one, or do you want to keep working at this one?
We can solve this.
Okay.
First, we should ignore W. First, let's prove.
Let's
GQ
first prove. Yeah.
Tangent.
Okay.
So you can hide the circle too.
Let me draw the altitudes.
Can you intersect MH with E prime F prime?
Yeah.
It's well known that F prime I equals to AE prime.
F prime I equals AE prime. Okay. So let's think about that. We have, so MF and ME are tangent to this circle. That's just like a well-known fact.
Yeah, because in circle.
Okay. Oh yeah, it's on this triangle. It's just upside down. That's why I didn't recognize it. But yeah, it's obvious. It's that well-known fact. Yeah, it's that upside down. Okay. SETF. Can we use projective somehow? Yeah, it looks a little bit like Pascal's or something. So we have so many intersections.
Can you intersect AQ with BC?
Okay. AQ with BC. Sorry.
Can you draw JG? Maybe it passes through as special point.
Let's see, JG. Maybe the midpoint of AH, like the center of the circle. Yeah, it looks like it. Oh no, not necessarily. Sorry, maybe this point is like, I'm just guessing stuff. Yeah, I'm not sure.
Can you draw from M perpendicular from M to BC and
Okay.
intersect it with E prime F prime? Maybe it's the point.
Okay. E prime F prime. It kind of, yeah, it does look like that's true. Let's see. Interesting. Okay. So I'm gonna make these all segments.
I guess it's not true. Can you move it?
Let's see. Sorry. Let me draw this line again. Yeah, it's not true. So let's see, TC for, no, we'd have MC is equal to Sj, I think. Should be true by similarity or homophagy. So Sj is equal to Bm is equal to MC, is that right? No, something's off. PM, I think PM is equal to Sj. Yeah. Okay. All right. So we wanted to see if JG passes through a special point. What if I try this? No. Yeah, if you want to keep working on this for a little bit, yeah, I'm happy to do it. But yeah, let me know if you want to move on. My brain is just tired today. All right. Yeah, let's see if we could try another one. Yeah, we can always come back. This one doesn't look, this one looks like it might not be too bad because
I think all problems are too hard.
but like this one, at least two of the pieces of information are like short. Yeah, let me just draw it and
prove that some circle is tangent to some other circle. That is usually very hard.
That is usually hard. Yeah, let's draw it and see what it looks like. just get rid of this. Whoops. I deleted the orthocenter. There we go. So this will be O, and then we draw a circle passing through B and C, and it intersects at F and E. This is F, and this is E, and then BE intersects CF at P. And PH cuts BC at T. And then we draw a line through T perpendicular to BC. And we want to see where it intersects the perpendicular bisector of EF. Okay. So a point J. And then we let PB and PC. So we draw the circle, this circle. We see where PB and PC intersected. We might have to extend PC. At N and M. Wait, let PB and PC intersect that circle. I don't get it. Isn't PMN? Oh, P doesn't lie on that circle. Okay, that's my bad. So it almost looks like CP. Yeah, I don't want it to look like CP's tangent to that circle. Yeah, maybe if I make it flatter, something like that. So we have this point and this point. So this is M and N. Yeah, this does look hard. We have to show that that circle is tangent to O. I mean, unless we can find like a special point. Unless there's something like obviously special about this point. So it looks like these meet on that circle. Actually, I don't think they do necessarily. So yeah, so.
I found the special point.
Oh yeah?
D lies on circumcircle AEF.
AEF, okay. All right. So let's hide some stuff that we don't need. Okay, so this is the perpendicular bisector of EF. We could just say J is the center of the circle. Okay, so we want to, Yeah, maybe this is a little more approachable. So basically we define D to be that point, and then we want to show that DMN, the circumcircle of DMN is tangent at D. So maybe we could do something with Hermaphrodites. So yeah, first we want to show PMDN is cyclic, and then we want to show its tangent.
PD, EF, and JT concur.
PB, EF, and JT. That's interesting.
Also, I think it is highly useful to draw in the center of BFEC,
Okay.
since that center lies on DP.
Okay. So they're collinear. And then JG is perpendicular to EF. Is it obvious that these concur, or it's something you noticed in the GeoGebra?
I just noticed it.
Okay. We can define the intersection of PG with EF and prove, yeah, it's perpendicular to BC. That's an interesting idea. Okay, so yeah, because that, well, yeah, so T is the intersection of HP and BC, and I is the intersection of GP and EF. We show that TI is perpendicular to BC. Yeah, that's like a sub problem.
I know how to prove that TJ and those two other lines concur.
Did you say AJ?
TJ.
Oh, TJ. How do you show it?
So intersect EF with BC.
Okay. Hold on just a second. Oops. All right. go. Yeah, I don't want M to overlap F, but I think that's fine. That's K.
Okay, then K lies on line AD by radical axis theorem.
All right.
And draw also the midpoint of EF.
Okay.
Okay. We see that KDLG is cyclic.
KDNG.
LG.
KDLG. Okay.
That is because of the 90-degree angles.
Yeah.
Also, JLTK is cyclic.
Okay. That also has two. Well, yeah, because the way J is defined. No problem.
Yeah. And also, oh, okay. I see we need just to prove also that JDTG is cyclic.
JDTG.
Yeah. I made a mistake. I thought that that was also like obvious, but I think it isn't.
Okay, let's see if we can prove it. JDTG.
If you prove spiral similarity center that which takes EF to BC, if it also takes I to T, then we can prove these 4 points are.
Okay. So let's see. I like that idea. So we want to show it takes I to T.
Also, how do we know ADG is 90 degree?
That isn't obvious, but it is a well-known problem. I think that one way to show it is to invert around BFEC.
Can we define AO intersect ABC? Okay. Yeah, that would lie, by what they just said, that would lie on that line. So yeah, this is going to pass through the antipode of A. Down there. Oops. But yeah, I don't know. There we go. I think that's fine. Ah, nice. Got the link. So here's the links Stefan just sent.
If we prove that pi and pH are isogonal, then we can prove the spiral similarity takes I to t.
If we prove what's isogonal?
Pi and pH with respect to FPE.
Okay. Be right back. All right.
Delete the last circles you draw.
Yeah, so this one, like this one and this one.
Yeah.
Let me make this look a little better. Got hungry. Sorry, I should have had it maximized. Wonder if Kn is tangent. Well, no, by symmetry. Actually, I wonder if is Kn tangent? No, it doesn't look like it. But maybe it passes through this point. No. Okay. Do you guys want to see if we can find something easier? Or do you want to keep working on what?
It's nonsense to solve easy problems.
Or what?
We don't need to solve easy problems.
No,
actually.
yeah, we don't need to solve easy problems. Yeah, we can just keep working through this. All right. Let's see. Okay, so Stefan, I think you said you wanted to show J, was it JDTG is cyclic?
Yeah. All right. So yeah, the center of that circle lies somewhere on OB. Let's draw the circle just for the heck of it. So yeah, I don't think these actually meet on the circle, but let's check. All right, see you, John. Have a good one. Yeah, this is a tricky one. You guys want to go back to the first problem? I feel like we were close on that one.
Let's continue this one.
Okay.
I agree.
Okay. So we want to show angle MDP equals angle MNP. But MNP is MFE. So we want to show MFE is MDP. So I think we want to show DFMI is cyclic. Is that true? Yeah. And DN, DI, and E is cyclic. Let's see, is that obvious? And then this here, this is cyclic. Yeah, I'm trying to think of the best way. Yeah, we want to show DINE is cyclic. All right. So yeah, showing that PMDN is cyclic is equivalent to showing DINE is cyclic. Let's see, is there some kind of angle chase or?
Can you check that if PT and PG are isogonal? With respect to BPC.
Okay, so we have angle BPC, PG, and PT. See if those are isogonal. Let's see. This and this. let's see, is this 52.07? Almost, but just barely. Oh no, they're both 07. Yeah, they're orthogonal. Interesting. It's a good. That's a probably really helpful.
It must be true. If we can prove it, then cyclicity is true.
Okay.
GITGIS.
All right. That's probably very helpful.
Was it the one or JDTG? What was the Stefan?
Oh, DINE was, or the one that Stefan said was
The one that Stefan said. What was it?
JDTG, I think.
Isogonal proves this.
Okay.
And this is very general. We just need P, H, and O, and A prime.
I think that proving, so we need to prove that PT is orthogonal to PQ, right?
Yeah.
I think then we should draw the altitudes of triangle and try to use orthogonal line lemma.
The altitudes of triangle PBC or
ABC.
ABC.
So like line BH and CH, those two lines.
Okay.
And try to use orthogonal line lemma somehow.
All right. Yeah, I just realized like a flatter triangle, it works better with the rest of the diagram. But yeah, for R and S, it makes them look kind of close to A. But I guess that's okay. So yeah, it is a very general figure, right? It reminds me a little bit of a different problem, but I don't think it's actually a generalization. Okay. So how are you thinking? So the orthogonal line lemma. Okay, because we have PH, PD.
Yeah, isogonal line lemma kills it.
Oh, really?
Yeah, let me tell it.
Okay.
So what did we prove now?
BH and BH, CH, A prime C and A prime B. We apply it on these lines.
BH, CH, A prime B, and A prime C. So use a orthogonal line lemma there.
Oh, I tried the orthogonal line lemma on BG and CG, so like with the center, and that didn't work. Yeah.
If we apply that, what I said, we get the lines from P to lines from P perpendicular to AC and AB, and they are obviously isogonal with respect to angle BPC, because angle PCF, angle PCE equals to PBF.
Okay. So the two perpendiculars from P to AB and AC are isogonal. That's what you're saying.
Yeah.
And then so you do those two lines, and then pH. Sorry. So originally, did you say? Okay, so pH. Yeah, write down in the chat before. Okay. Okay, yeah, that's what I thought you said. So BHCH. But like for the isogonal line lemma, shouldn't it be like 4 things coming out of one point? Like I guess that's like a quadrilateral, right? BHCH. BH intersect CA prime. Okay.
Oh, and we have points of infinity and then the parallels. Yeah.
Okay. BH intersect. Okay.
We actually apply it on PH, PA prime, PB, and PC.
I think I see what you're saying. Okay.
So we do have that PT and PG are isogonal.
Okay.
So what do we get from that?
I will write the angle tracing.
Okay. Yeah, because you're starting with H. Yeah, I think this is like the parallelogram isogonality lemma, right? It's like a degenerate case of the isogonal line lemma. So basically, we know that HBA prime C is a parallelogram. Okay, so then we have angle DTI is equal to angle DKI. Okay. So yeah, we wanted to show JDTG is cyclic. But I feel like it has to meet, it has to, I feel like it's at least somewhat helpful if these are isogonal.
It should be helpful because we figured out how to use the condition that H, that line PH. I think that was the most problematic point, line, I mean, in the whole problem.
Yeah. Yeah, so basically since P, let's think about this. Yeah, we have a parallelogram here.
Okay, I saw it now. ADI equals to KTI. They are both 90 degrees. Because of the definition of J, Tij are collinear.
Okay, so you just basically proved that J, T, and I are collinear.
Could you repeat how you got that?
If the spiral similarity from D takes I to T, then we have dk Ti are cyclic. Then we have KTI is 90 degrees.
Interesting.
Oh, so we proved that I goes to T by spiral similarity. Yeah. But how does that prove that those are collinear?
Because we have KTI is 90 degrees. Because from spiral similarity, dk Ti is cyclic.
Yeah, so this would be cyclic, which would mean that IT would be perpendicular to TK. And then we know that JT is perpendicular to TK, so that would prove that those are collinear.
Oh.
And we know about the spiral similarity because does the spiral similarity follow from the isogonal lines?
Yeah, because FECB is cyclic.
Okay.
This gives FPE with I is similar to BPC with T.
Okay.
Angle condition.
Okay. Wow, there's a lot going on here. Okay, so we know that Ji and T are collinear, which is good to know.
Can you check that if MN is parallel to BC?
Okay. It looks like it. Let's see.
That should be by Rimes theorem. No. Maybe. Yeah,
Because,
I think it is Rimes theorem.
yeah. We just have angle PNM is angle MFE, which is angle sorry, I had it for a second. Which is MFE, which is CFE, which is CB. And so yeah, it's just Rimes theorem. Yeah.
Intersect TI with AB.
This point?
Yeah. Then by angle tracing, DUIM is cyclic.
Okay.
So we have another point on that circle, and we should prove that F also lies on it.
Okay, we know DUIM is cyclic. We want to show F also lies on it. Okay.
Well, we know BF UI. Do we know M is on that?
We know M is on this. We want to show F is on it, right?
Oh no, I
Because
think that we know F is on it, and we should prove for M.
Okay, let me go back to what I was thinking before. Yeah, because showing BIMF is cyclic basically solves the problem.
wait, how do we know tangency after proving it?
Oh, actually, no, you're right. We still have to prove tangency. Yeah. So yeah, basically we show that these are isogonal. Now we want to show that that actually is also equal to angle KDM, I believe. So let's see. Is that right? If they're tangent, then this angle
They are not equal.
are not equal. I wonder if it picked, but I wonder if it did angle F. I wonder if it accidentally did point F instead of point M. Like, what if I did? Let me just check. Oh, but I got to see the other point to do it. Let's try this. Oops. KAF BPT. Yeah, no, these aren't equal. So oh yeah, because this wouldn't be the tangent. If they were tangent, this wouldn't be the tangent line. Yeah. Let's see. I'm just trying to think how, like, yeah, we haven't proven that it's cyclic yet, but I'm just trying to think if we did, how would we show its tangent?
Looks like DUNTB is cyclic.
DUNTB. It's a lot of points. So as far as DUTB, so we're saying angle UDB is 90 degrees. Let's see, is that obvious?
Oh, actually, that part, DUTB, is obvious because of the spiral similarity.
Okay. So yeah, so we'd have to show that n lies on it. And so basically we want to show angle DNB equals DUB.
Serdar, so basically we know that DUIF is cyclic, and we know that spiral similarity at D, that spiral similarity sends Fi to BT, and that proves the cyclic.
Oh, did we prove DUIF was cyclic, or you're just saying once we know that it would follow?
We know that.
Oh wait, if DUIF is cyclic, then that proves that DMPN is cyclic, right?
No. Oh, actually,
I think it.
DMPN.
Yeah, I think by an angle chase that shows that this is cyclic, like because.
Why?
Because then angle PMN. Let me think about this. Or at least I thought that I saw this earlier. Angle PNM, we want to show that's equal to PDM. Let me think about this. But PDM is IDM.
We don't know M is on it.
Oh, we don't know M is on it.
Yeah, we are trying to prove M is on it.
Okay. Yeah, somehow we have to use that JM equals JN. Or I'm sorry, JE equals JF. I wonder if the spiral similarity takes M to something interesting. So it'd be like a point right here. No. Okay, so yeah, and do we know where N goes under Yeah, I don't know.
I guess I found it. I will write it. See if
Okay.
it's true in the chat.
All right. So I guess what part of it did you prove? Did you prove the whole? Did you prove that this is cyclic, or
Yeah, M is on it.
M is on it? Okay. All right, I will check
Then
it out.
we need just to prove that that circle is tangent.
Yeah. Okay. Wow, this is one really super problem. I can't believe we made it this far. Let's see if we can prove the tangency.
Okay, I assumed M is on it, then I proved M is on it. But
Oh, you assumed M is on this circle?
yeah, my proof is wrong.
Okay.
Oh, actually, a bit of progress. I mean, we haven't proved that it is cyclic, but if we knew that it is cyclic, I just checked, and that circle looks like it stays the same under inversion around BFEC.
Interesting.
And
So,
that would mean that that circle has to be tangent also to BPC.
okay. So if we invert it around this, it just stays the same. It's fixed. Okay. So that means it has to be tangent to BPC, is what you said.
Yeah, since D inverts to P around that inversion.
Well, is that true? So let's think by homophily, because we know that this is similar to this. So are they just tangent by homophily at P?
From parallelity.
Because Mn is parallel to BC.
Yeah.
Oh yeah. So so that part of tangency is not hard. So we just need to prove it is cyclic then.
So wait, once we know that these two are tangent, does that prove that this is tangent to the whole thing?
Yeah, because of the inversion, since P inverts to D.
Okay. All right.
And
Makes
that's
sense.
also, yeah.
All right. So that's where that's where we use that Mn as parallel to BC.
Which inversion with respect to which circle?
BFEC. Oh, actually, we need to prove that PMN stays the same under the inversion.
This circle, we have to show that it stays fixed under the
Yeah.
inversion. So basically, like we want to show that GP times GD is GB squared. Maybe it's just an angle chase because basically we want to show angle GPB. That would be the same as showing angle GPB is angle GBD.
Oh, that I think it is not like obvious, but
Yeah.
it is a well-known fact that P and D invert to each other.
That this circle inverts to itself.
I think it will mean that, yeah, because P inverts to D and the D inverts to P.
Okay.
I think that the proof for that would use Brocard's theorem or something like that. Poles and polars.
I was thinking though that there might be, because showing that it inverts to itself, it's the same as showing that GP times GB is GB squared, okay? And that's the same as saying that, proving that angle GPB equals angle DBG. And I wonder if that's just like an angle chase or something. Especially because we know angle GPB is angle TPC from the isogonality that we said before. So yeah, let me check that. So TPC, and then whoops. Oh wait, those aren't equal. Oh no, I need DBG, sorry. Not T. Yeah. So can we show that those are equal? So this is the same as this. But yeah, this is just angle DBC plus angle GBC. And yeah, I wonder if you can just chase it. But yeah.
You probably can.
Okay. Because yeah, this is angle, this is this angle. Yeah, most likely. So yeah, basically, if we can show that M lies on this circle, then we would have solved the problem.
Can you also define V similar to U, intersection of TJ with AC?
TJ with AC. Yes, one sec. So this is V. Whoops. So it would be DVIEN would be cyclic. I guess we could do it for a couple more minutes just because I started later.
I proved that N is on that circle.
Oh, really?
Yeah, it's from spiral similarity center that if you intersect BE with circumcircle of ABC, can you intersect?
Yeah.
Then angle DNU equals to DWA and it equals to DBA and it equals to DBU. Thus N is on that circle.
The N is on this circle.
No, n is on circumcircle of DUTB.
Okay, so this one is cyclic. And then by the spiral similarity, okay, you prove that n is on that circle.
Serdar, you have proved that n is on circle DUTB, right?
Yeah.
I think then by an angle chase, we get that DINE is cyclic. So that should be done, I think, if we have not made a mistake.
Okay, so you think once we know that these are cyclic, then that shows that DINE is cyclic?
Yeah, I will just write an angle in the chat.
Okay. Yeah, you could write it on Discord. But
we are not finishing this till we solve this problem, right?
Yeah, we are here.
You want me to write it up, the solution here?
I think we should just at least see if our solution is correct. So
Okay.
I finish this because we're really close.
Yeah. Let's just check that it's correct. So yeah. All right, let's see. DNE is 180 minus DNB, which is 180 minus DUB, which is 180 minus DIF, which is DIE. Oh yeah. Yeah, you guys have the same angle chase. Yeah, so that's it. So once you show that n lies on that circle, so where did we use that J lies on the perpendicular bias? I guess we had to use it somewhere. Yeah, in this whole thing. So that should solve.
Actually, we didn't just prove the tangency, right? So we will use it.
Okay.
Serdar,
prove the
could you
tangency?
just we have proved the tangency, but could you just tell again how you proved that n lies on that circle?
Spiral similarity at B, taking UN to AW. Then we see DNU equals to DWA and it equals to DBU.
So the spiral similarity takes U to W, is what you're saying, right?
UN to AW.
UN to AW.
And where did we use point J?
I assume that n is on that circle. I guess it's wrong.
But we're just one step to the whole solution.
We're very close. Yeah. All right, I think I'm gonna stop now, but thanks for sticking around till the end. And yeah, I hope you guys have fun solving the IMO shortlist problems. So yeah, again, thanks to Serdar for sending me all the problems we did today. And for anyone watching, if you want to join this session, feel free to email me at mgreenby801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So thanks and have a great day.